So I'm Eric Robinson, and I'm here to talk about a solar-powered cannon for delivering satellites in space to from the Earth to the Moon, from the Moon to Mars, and from Mars to orbit. So, so let's talk a little about the history of launch systems. Everybody's using rockets nowadays. It's the only way to get from Earth to the Kármán line. But we do have another opportunity to use something called kinetic launch. So this is an illustration of it, but in real life, this exists. It's in the desert. It's in Yuma Proving Ground. It's 54 feet long, and we've shot up to about 30 kilometers vertically with it. We've shot about Mach 6, so we're hypersonic already going horizontally. And the original idea was Jules Verne, right? He wrote this book, From the Earth to the Moon. And this book was about putting people in a cannon and sending them to the moon. Well, there's a couple little problems with that. One is the G-force, and also you picked the wrong propellant. So the right propellant is actually hydrogen. Hydrogen is the fastest propellant that we know of. At this point, the record with hydrogen is 11.2 kilometers a second, which is escape velocity. If you can get through the atmosphere at 11.2, you just keep on going. And so, so the other problem with rockets, the main problem with rockets is the small amount of payload, right? How much payload can you get in a rocket? It's like 2, maybe 3% if you're Elon. So that's about all you can get, 3%. Well, how much can you get with a projectile launched with hydrogen with a small rocket to circularize the orbit? Once you get up there, you can actually get 10+% payload. So you got maybe 5 times more than you'd expect with a regular rocket. And so we do have to deal with the G-force. And so if you guys want to go outside, that'd be great, because I can't quite hear what I'm doing here. Maybe you want to talk outside, that'd be great. So yeah, so we're trying to figure out how can you deal with the G-force? Well, things that are compressible, like fluids, that's fine. There's no problem at all. You can shoot those all day long. Building materials are good. Water is good. And actually, most of the thing that goes on a mission to Mars is fuel. So 90% of the mission, the weight already is fuel, right? So we can shoot fuel to orbit. And Elon wants to be able to fuel in orbit, so we could become the fuel station for orbit. So the history of kinetic launch. So right now, the Gerald Bull actually owns the world record for shooting vertically. That was with gunpowder. So gunpowder, he got up to 180 kilometers with gunpowder in 1966, and no one's beat that record since. So we're going to try to take that record eventually, and we are shooting from the same location where he set that record at Yuma Proving Ground. So we're about 3 times, hydrogen's about 3 times faster than gunpowder, so we should have a physical advantage there. And the next thing is, well, who's got a history of shooting guns this fast? So there was the system that Gerald Bull used was called HARP, High Altitude Research Project, and that did go vertically, and it did set the world record. And he did get to the above the Kármán line, obviously, because he went to 180, and 100 kilometers is the Kármán line. So he was actually in space, but he never got to orbit. He got up into space and then came back down, made a big hole in the desert. So that was, I don't think he parachuted anything of his down. It was all, it just went into the dirt, and they had to dig them out. So we are planning to parachute ours back down. So our first mission that we've been tasked with is to go up and sample the mesosphere. So right now, the mesosphere is 36 to 70 kilometers up. And so we've been tasked to go up there and check out what's going on up in the mesosphere, because it's important. A lot of meteorites are coming into the planet every day, and most of them burn up in the mesosphere. So there's metal up there, and there's also a lot of different isotopes of oxygen up there. And so people are really interested in finding out, because the global Earth budget, people are all concerned about climate change. Well, you want to know what's actually happening. You need to know what's happening in the mesosphere. So it's too high for balloons. It's too low for satellites. And rockets themselves, if you use those to get up there, you create your own pollution from the rocket. So you kind of contaminate your sample. So what we're going to do is shoot a vehicle up into the mesosphere. It's evacuated. We're going to open the cylinder, suck air, whatever's there, close it, and then parachute back down. So we're being paid by the National Science Foundation and a couple of pretty famous chemists. This guy, Dr. Thiemens, he's a Lawrence Award winner, and another guy, Dr. James, who's at Harvard. So those are the two guys are going to use the sample once we get it down. But anyways, this is kind of a so kinetic launch is real. Light gas guns are real. Gas guns, gas cannons are real. And so the other part of the history is our CTO. I mean, our technical officer is John Hunter. So John Hunter actually built the SHARP system that was at Livermore Labs. If you look up SHARP, SHARP, on the internet, you'll see what that is. That system was shooting Mach 9, and it was testing scramjets, but they never actually got to go vertically with it. They just went horizontally. So we made John's dream come true, 25-year-old dream come true. We shot vertically last December and got up to about 33 kilometers vertically. So that's kind of the history of gas guns and our group. So this is a plan that we have. So John Hunter is the CTO. I'm Eric Robinson. That's Rob Fryer right there. And Don Whitney, historically, we met Don Whitney at a Mars conference. He actually kicked in the first money that started us. So you too could become an investor in Green Launch if you're interested. You can follow Don Whitney's path forward here. All right, so good. So let's see. So the first phase, this is a solar tower. This is like Ivanpah. If you've been to Las Vegas, you may have seen this on the road going to Las Vegas from Los Angeles. It's a series of mirrors that irradiate a tower. They heat a fluid there, and that fluid can then be used to create energy. I guess I can go to this presentation. Sure, there we go. And so this is, we're marriage on Mars. We're going to marry the solar tower with a hydrogen cannon. And so this just gives some of the analogy of what kind of solar power you can get off of Mars. You're going to drive a two-stage hydrogen cannon. Hydrogen steam is recaptured. So this is like on a regular, gun with a silencer, you can catch a lot of the gas coming out of it. And in our case, we can catch above 95% of the hydrogen. So not only is our propellant really the speed is great, but also it's reusable. And so we're gonna launch it at 4 kilometers per second. So the escape velocity from Mars is about 5 kilometers a second. So on Earth it's 11.2, Mars is about 5, but to orbit from Earth is about 9.5 kilometers per second. And to orbit from Mars is 3.3. So we're going to launch at 4 kilometers a second, and we're going to put propellant into orbit there. Got to get my fingers up. So here we have some of the components in this tower. There's the power to receive the power, a steam accumulator, and these are heliostats, and there's the pump tube. This thing's very touchy. If I can find arrows here. Let's see. So this is what the system looks like. I don't know if I could tab. So steam accumulator, there's a piston. So once we have this steam accumulated, the pressure starts to build up, the piston is released, pins are broken, and it flies down the tube. It compresses the hydrogen in the tube, and then it launches that projectile up the tube and out through the muffler and into space at 4 kilometers per second. Boy, this is really touching. Okay, maybe I'll go back to the other scheme. Go back to this way. So here's a view looking down at it. I don't know who Bruce McKenzie. Is there a way to get this screen cleared up here? I've got Bruce on here for some reason. Shouldn't that be me up there?
I don't know what I did to be there.
Oh, no, but isn't my face supposed to be on here somehow?
Owen?
Oh, there I am. Okay.
Okay.
No, me and Bruce, that's good. We're both together here. All right, very good. So again, looking down on this, the power tower, the launch tube, and the support for the launch tube. Oh, I think I found an arrow down. It's another arrow. No, I wish I could find out a way to do this. Let's just enter. You can do escape tab. Backspace. Is there a way to push this forward, like automatically to go from slide to the next?
Yeah.
Oh, there we go. Very nice. Very nice. Thank you. Okay, so here's the support structure for the launch tube. And you can see the little truck there. That's for scale. So this is a big system. And in this case, the launch tube in this diagram is a little bit higher. From Mars, we don't need to have such a high angle in our launch tube. We can launch almost horizontally, about 6 degrees off of horizontal, and we can shoot right to orbit. Here's what the heliostats look like. And they're adjustable in 2 planes. You can make them go up and down and side to side. Elevation, azimuth. Here's a cutaway view. We have a reaction mass in here, so that is to help keep this thing stable. The reaction mass is going to push forward and push water into another chamber, which is totally recyclable also, but the water acts as a brake to slow down the reduction, the mass here. And the Sharp system had rail cars full of bricks or weight or whatever, so that when the Sharp system shot, the reaction mass went the other direction, so it was totally stabilized.
How loud is this thing?
Well, let me tell you about this gun. When this thing shoots, it's loud. You're behind 3 inches of steel and you've got earplugs in, but the whole place shakes. I mean, imagine this, this tube extending into the sky, right? And you can hear the pumps pump, and you can hear this pressure building and building inside the tube, right? So in the combustion area, we're doing a combustion gun. This gun is just going to be compressed. It's going to compress the hydrogen. It's not going to ignite it. It's going to compress the hydrogen and release it out the tube. And what goes in there comes out like it's a super blowgun, basically. And so when we shoot, we use a combustion gun. We mix hydrogen and oxygen together. And we have ignition, a stick we call the Christmas tree, which is a whole bunch of ignition EBWs, electric. They're going to be there's time nuclear igniters that ignite it all simultaneously, because we don't want to have a erratic burn. We want to burn very evenly, very smoothly, and then when this thing ignites, it goes to 7 times pressure. So we're 4,000 psi in the chamber. Go to 28,000 psi. It breaks the disc, and out comes this projectile like. It's screaming, and it's loud, it's exciting. I mean, you think rocket launches are exciting. This is exciting. Yeah. And if you want to get to be part of this project, let us know. We can give you a business card. I've got a few here. So again, kind of a close up. Here's the sabot, which is around the projectile there. That holds it in the gun as it's being released up the tube. It holds it centered and keeps the pressure behind it even. And we do have some intellectual property to try to maintain that pressure a little bit longer. So that's our IP moving forward. And there's the muffler system, which is kind of like the silencer, and it's going to catch at the very end of that, slows the gas down. At the very end, there's an iris closes, it catches all your gas, so you can pump 98% of it back down the tube and use it over. Here's the sabot coming off the projectile, and multiple sabot petals traveling at a high velocity. Here's the kind of close-up of the sabot with the petals. Okay, here's our payload. The brown is the payload. We have a small rocket motor on here, because you need a rocket motor when you get to the top of the apex to be able to come around and to start orbiting. So you've got to circularize your orbit. So that's what that rocket motor is for. We've been working with Northrop Grumman to develop a solid rocket we can use on our system. And here's kind of the bottom line of this thing. So this, you can see, so we're launching at 4 kilometers a second here, and it goes through a little bit of atmosphere on Mars, like 1% of what we got here. This is when the rocket fires out here, and we continue into 3.3 is orbital, 3.3 kilometers per second is orbital on Mars. And then the other graph there just shows the altitude as it's coming out of the gun and then circularizing into orbit up there. So the bottom line is green launch only uses 8% of the launch vehicle mass. So we only need 8% instead of 70% of the rocket mass for propellant on Mars. Like at Earth, it's 98, 99, 97, 98% rocket is mass, just getting the thing up there. So you only have 2% payload. But in our case, on Mars, we're going to be able to have, like 92% payload. So it's going to be a lot better on Mars because there's thinner atmosphere and less gravity. And then got one more picture here. So this one Rob wanted me to add to the pictures here. This is Phobos. So Phobos may be our next station, our next gas station. We could put it in orbit up there. Phobos was the son of Ares. The moon has got about a surface area of about 1,500 square kilometers. It's about 6,000 miles or 9,000 kilometers above the surface of Mars, or from the center of Mars. It goes around every 7.5 hours, so it goes around pretty frequently. You have plenty of opportunities to jump on and jump off of it. And so if you jumped off of Phobos, you could jump 12 feet in the air. So you could do a lot of tricks off Phobos. You're only going to weigh about 3 ounces. So, and if you jump in the air, you're going to wait 12 minutes to come back down. So you got to be careful you don't jump right off Phobos. And so the I've heard a couple of things about Starship. It may or may not need to refuel. I mean, from Earth, I think it needs 8 to 12 fuel runs to get enough fuel to go on to Mars from launching from Earth. But I'm not sure if it's going to need fuel coming in from the surface of Mars or not. But anyway, we've got other things like we talked to Buzz Aldrin about a cycler in the past that would go from Earth to Mars all the time, and so you might want to have this be your fueling station to kind of pop off and fuel it as it goes past. But anyway, so that's the final slide. If you've got any questions, please let me know. Yes, sir.
How big an area of solar collectors do you expect to need, and how long is the launch tube going to be in your design there? And also, how much hydrogen would you lose on each launch, the 2 to 3% that you were talking about?
Yeah, so I think it wouldn't be let me see if I've got any of the math here. I can probably get a little. So here's the tower. So the one I think at Ivanpah is about like 700 mirrors. It's a lot of mirrors. It's a lot of surface area because the solar radiation on Mars is, I think, 1.5.
How big would each of those 700 mirrors be?
Oh, let's see. Let's check that out. Let's see if we can see these guys here. So yeah, these heliostats, I think they're about like 12 by 12, maybe a little bigger. These are. I can probably get you that information.
So roughly, or maybe 100,000 square feet of solar panels.
Yeah.
And how long would your tube be, and how much hydrogen would you expect to lose before you go?
Yeah. So this launch tube. So if that's we talked about this thing being a truck here. Let's see. Like it's a long tube. The one that he ran at Livermore, like that's a truck there. So this is obviously going to be a pretty long tube. I think that Livermore Labs. That was, I think, 400 feet long. That included both the compression, which was the area where you compress the hydrogen, and then the launch tube itself. So we're talking about, a decent sized tube here. The place they were thinking about doing this was up at Adak, which is one of the islands in the Aleutian chain, because the mountains are about the right angle there, and that would actually go right to the space station. That's about the right azimuth for a space station. But yeah, I can get you some more information on that. I'll give you a card. Anyway, yes, sir.
Would this work well on Earth to reach orbit? Could you launch like fuel to orbit?
Yeah, that's actually our initial plan, is to launch. We're going to, after we do our atmospheric sampling, we're going to be doing small, like CubeSats, like a pea pod of 3 CubeSats to orbit. So we can do it for about half the price of a rocket launch. And so again, the complicated part of it is you got to put a small rocket at the end of it to get yourself circularized once you're up there. So yeah, this is definitely the plan, is to shoot from Earth originally. Earth initially, and obviously the moon, it's nothing. I mean, so this, we could, like I said, the record is 11.2 kilometers a second, but if you shoot that velocity, you wear the barrel out. So we have to stick it around 6 kilometers per second. So we're still like 3 kilometers additional we need to add to get to orbit, right? So that's where the rocket comes in. It's 3 more kilometers per second. Yes, sir.
How much difference would it make? You're launching at, well, you're actually about 4,000 feet, maybe launching. What if you were to launch it off Mount Kenya? On the equator, right?
Yeah. So it's about 10% of the launch velocity that you would be able to, you'd be more efficient. You wouldn't lose 10% of your friction going through the atmosphere. But for us, our velocity isn't the question. We've got plenty of velocity coming out of there. So we're okay. We're okay to get through the atmosphere wherever we launch from. Yes, sir.
Looking at your scale there with a little chart, this is quite a large structure to build on Mars. We propose that it's have to find a volcano.
That's right. The biggest volcano in the solar system is right there. Yeah, you may be able to use something, use a natural feature, the edge of a crater or something like that. But yeah, this is
on.
Oh yeah, it would help to put it right on the equator itself. So the ones that we have here is actually it's storage at Davis Motham's Air Force Base over there. It's been put in mothballs. That was the Sharp system, and so it's steel, and it's segmented too. It's in sections, so you can load it and you can reassemble it.
Gun.
Oh yeah. I mean, this gun was shot throughout the 90s. You can look at the history of the Sharp system. So that was a segmented launch tube. And it was disassembled. It's like I said, it's over here at Davis Motham's Air Force Base. Yes, sir. So in this one here, this thing is totally scalable. So it could really be any size you want. I mean, we've looked at systems up to 1 kilometer in length. There would be in the ocean, and just the muzzle will be out of the water. But so that way you could move to any angle you wanted to in the water. And so yeah, there's different. I mean, it is totally scalable, so it doesn't matter. The initial ones he built were a couple of feet long, small diameter ones, and then just everything scales up perfectly.
Sharp was 4-inch, I believe, and that you would be around we've got 7.
Yeah, it's 175 millimeter, which is a little over 7 inches in diameter that we're shooting right now. Go ahead.
It's curious. I've seen maybe a competitor's launch system that it's basically a giant centrifuge to throw an object up. Would you say what are some pros and cons of each, versus your sort of launch system? Yeah, so the pro is that they're getting a lot of good funding, which is great, and they're also proving you can withstand G-force. That things can withstand G-force of launch. They're spinning for about an hour. We're shooting for 40 milliseconds in the tube. So our exposure to high G is a lot less than theirs is. Yeah, I mean, there's nothing faster than hydrogen. I mean, you can't spin anything this quick. So yeah, it's great that they're in the same bailiwick that we are. I mean, the kinetic launch is what this is called basically. And so they're an interesting comparison. Thank you for bringing that up. Thanks for that.
You're welcome. Any more questions on this? Okay, anybody wants a business card, let me know. I can get more information. You can go check out these videos online. You can see 10,000 frames a second, what something looks like coming out of the barrel. Yes, Rob.
Question. Well, what about asteroids? What about the moon? This works more easily in vacuum, small gravitational fields.
Yeah.
So as we get out there, this may become the preferred method of sending mass from one point.
Oh yeah, because our propellant is like you shoot a rocket, your propellant's gone. This propellant is 98, 99% recyclable. So we save propellant. Like say you want to go to Mars. Well, I think even to do the Sabatier process, you have to take the hydrogen with you, right? You can use the atmospheric CO2, but to make the methane, you need to have hydrogen source. So you've got to either find water and crack it, or you got to bring your hydrogen with you. And the original theory that Bob Zubrin had was to take the hydrogen with you. We need to take a lot less hydrogen in this case because you can just recycle it over and over again. Yeah, and from the moon and from asteroids, I mean, this thing is a mass driver. That's what this really is. It's a super mass driver. And so from the moon, this is like, that's just a walk in the park for us. We've got plenty of velocity to get off the moon. All right. I've got cards. So take a look at these. You can go check out these videos. They're pretty
Did
interesting.
you see the Gerald
Thank
Ford
you.
movie, Armageddon Gun?
Yeah.
Boy,
Yeah.
that is really, of course, his bore was only a meter,
Yeah.
small caliber there.
Yeah. He's an interesting guy.